and that's going to be by Ciaran Ryan Anderson. He'll be speaking about implementing fault-tolerant entangling gates on the 5-qubit code and the color code. Okay, thank you.
Ominous black screen. Okay. All right. Quantum error correction's hard. Classical error correction is already hard too. All right, yeah. So today I'll be talking about logical 2-qubit gates for both the 5-qubit code and the color code. Go. All right. So being a quantum error correction person connected to a company that develops hardware, you have to worry about not just designing large-scale fault-tolerant schemes, but also pushing the current devices forward, because you have to start somewhere. And, of course, pushing the software forward as well. And, of course, we need to hit, break-even milestones, continue to scale up, look at more logical qubits, and so on. And Natalie has already discussed some of these works where we kind of, given the resources that we currently have, we sought out to do all sort of the recipes that you would imagine needing to do for large-scale quantum error correction, limited to, for example, 10 qubits. And as Natalie alluded to, we're constantly improving these traps. So she talked about like the Steen code, a single logical qubit, but we also have this H1-2 trap. Eventually we had 12 qubits in the trap, which enabled us to actually start looking at 2 logical qubits and doing a logical 2-qubit gate fault tolerantly. In particular, we could get away with doing a fault-tolerant C0 gate with the 5-qubit code. Of course, each code block has 5 qubits, so that leaves around 2 extra qubits to do syndrome extraction. And this is just sort of a reminder of what the 5-qubit code looks like. It has stabilizers that are kind of cyclic in nature. You have access to all single-qubit Clifford gates, although some of them require permutations, although that's not such a big deal for us since we can move qubits around. Okay, so the 5-qubit code is not a CSS code, so therefore it doesn't have necessarily this nice transversal C0 that you have with like the surface code or the color code. However, with just 2 code blocks, Yoder et al. In their paper about peaceable fault tolerance showed how to do a fault tolerant 2-qubit gate for the 5-qubit code. It did more than just the 5-qubit code. They talked about peaceable fault tolerance in general, and it was also an interesting paper in that it talked about like other methods to kind of allow you to have a universal gate set. But we concentrated on this for now. And so while this code doesn't have a transversal C0, you can basically apply physical C0s in kind of a round robin sort of way in order to apply a logical 2-qubit gate. However, it turns out that like if you have a single error event happening, which you're supposed to be able to correct for a distance 3 code, then those error events can propagate badly through the circuitry and lead you to, like, for example, here, a weight 6 poly error. And so if you do syndrome extraction after that, you don't have enough information to recover, and that's bad, so it's not fault tolerant. However, as the name implies in peaceable fault tolerance, if you break your gate up into pieces, you can insert syndrome extraction in the middle and actually recover enough information in order to come up with corrections. So that's what we aim to do. Also, I should note that because we're doing part of the gate, in the middle where we're doing the syndrome extraction between these 2 pieces, the code blocks are partially entangled with each other. So you have stabilizers that kind of live on both code blocks. It becomes a 10-to-3 code in the middle of this, this computation. And so to do this, the syndrome extraction, the QEC gadget in the middle fault tolerantly, we kind of borrowed the same sort of ideas from the previous Steen code work that Natalie talked about, in which using ideas from Reichardt, where we measure each one of these stabilizers one at a time using a flagging circuit. So we have both the syndrome ancilla and the flagging ancilla. And we measure these one at a time, and then as soon as we see a non-trivial result, kind of like with the Steen code, we then branch over and remeasure all the checks using unflagged kind of normal circuits. Otherwise, we continue down this process, and if we see a non-trivial result, or they're all non-trivial results, then we're good. We didn't detect an error event. However, if we did end up being over on this right-hand side, then we send in real time this information to a decoder to come up with corrections. You don't have to know all the details of the circuitry, but I'm just kind of pointing out that this is a rather deep circuit. It requires around 200, or not 200, 100 2-qubit gates in order to enact this QEC gadget. That's quite deep. To do fault-tolerant initialization, we use the scheme by Chow and Reichardt, in which you're using the encoding circuit, and then similar to the Gato scheme, you measure different representations of the logical operator, and then as soon as you see a non-trivial result, you know something's wrong. So you either post-select on that, or you do repeat until success like we did with the first Steam code paper. And then the fault-tolerant measurement scheme by Chow and Reichart is basically the adjoint of that, except it's far more complex because you have all sorts of rules based on like if the flag went off, then you branch over to the end and do the coherent unencoding or decoding circuit, measure the syndromes and come up with the correction. Otherwise, you continue, and there's steps about if that flag went bad or the the two measurements aren't the same, and so on. And it gets more complex, and it looks a little crazy. You also have to like negate previous syndrome measurements that you made, and I don't always write code perfectly, and so that's kind of how I felt like whenever I was trying to debug things. Anyway, so both for the QEC gadget in the middle of the peaceful fault-tolerant gate, as well as this coherent decoding circuit at the end, we're using this real-time decoding using the hybrid compute system that Natalie discussed. So we write our decoders in Rust. Or you can choose another language like C or C++. And there's also additional logic of like negating previous syndromes and that you were measured if you're doing this decoding at the end. Anyway, this is sort of an outline that Natalie basically showed. We write this chasm separately from the WASM. The chasm makes function calls. The WASM side kind of has a virtual machine, so has a stateful classical environment that can store like the polyframe and so on. This all gets sent to the device. They all run in parallel, and of course, at the end of the day, you get syndromes out or measurements out, and you can figure out the performance of your algorithm. Okay, so I went over a lot of stuff. But kind of zooming out, the general experiment looks something like this, where we're like initializing two different blocks. We potentially do this fault-tolerant check to verify the state, do some sort of logical rotation, basically transversal gate, their peaceful fault-tolerant gate in the middle, doing a logical C0, and then this logical rotation at the end and doing a fault-tolerant measurement. These green boxes indicate places where, this overall experiment is around 200 2-qubit gates, so it's getting kind of quite expensive to just do a simple thing with this code, but we're qubit limited at the time. And these green boxes indicate where we kind of reduce the complexity. So we kind of thought it would be interesting to look at if we reduce the amount of fault-tolerant gadgetry utilized in order to see how the performance worked out. All right, and then these are basically our different initialization settings and kind of sort of indicating the measurements that we'd also make at the end. We kind of wanted to show that the logical C0 is performing like a physical C0. So you want to see these transition rules. So for example, if the input qubit is a logical 1, it flips the target. And similar story with the X basis. And then it turns out that you can have different X and Z input states. If you look at all different combinations of those, then you get all different combinations of the Bell states. So then we can measure logical XX, YY, and ZZ and make sure the statistics are as we expect from the Bell states. Okay, so then you end up with this giant plot. The x-axis indicates the amount of 2-qubit gates in the total amount of 2-qubit gates in these various experiments. Each vertical kind of line is a particular kind of experiment with a certain amount of fault-tolerant gadgetry used. The red or boxes, box points, are the X basis. The blue or triangles are the Z basis, and the green or stars, I believe, are the Bell state experiments. And then the solid lines are the actual experiments. The dotted lines are the emulation or the detailed simulation of the device, and you can see that they're fairly close to the device. Of course, it'll never be perfect because there's drifts in experiments, and you never know exactly what the error model is. But we can see that they reasonably agree. I also should mention the y-axis is fidelity, but that's just the inverse of the additive inverse. So 1 minus that is the error rate. experimentalists tend to like to talk in terms of fidelity. Okay, I won't go through all these different points. I'll just highlight a few. So this point all the way on the right, or set of points, is the full fault-tolerant gadgetry version of the experiment. We can see that the completely random is around 25% fidelity. So we're above that. For the X and Z basis, we're around 70%. For the Bell states, we're around 50. And then if this set of points represents, we take that syndrome extraction, or the QEC gadget in the middle, we only do one syndrome extraction round instead of potentially up to 2, and we don't do any flagging. So you're just using the non-flag circuits, and then we decode and apply corrections. Then we unfortunately get better fidelity. So that's a little sad, but maybe to be expected given the sort of error regime that these experiments were done in, as well as the amount of 2-qubit gates. So it's important to understand your noise model and think in terms of the complexity of circuits. And then if we stripped out all the fault-tolerant gadgetry, we get this C01F thing. So we're just using the encoding circuit. We're just doing the round-robin style gating without any syndrome extraction in the middle, and we're just measuring the logical operators at the end. And we get that, and they're around the 90s percent fidelity. So kind of sad that things got better and better the less fault-tolerant we got, but that's life. But we're continuously improving these traps. Once we fabricate them, that doesn't mean that's it. And so Natalie talked about when we had H1-1 and with only 10 qubits in the trap. And I think at the time only had three gate zones active. So eventually after the 5-qubit experiments, we had an upgrade to H1-1. Also fidelities are continuously improving. They do better optics and so on. And yeah, so with 20 qubits, that kind of unlocked the ability to do simpler things with the Steen code or the distance 3 color codes. So now we can actually do the transversal gates. So I won't go into all the details of the different gadgetry. Natalie, we basically use the same sort of procedures as we did with that first Steen code paper, but then we just did that for 2 logical qubits and with a transversal gate. So essentially, yeah, we're initializing 2 blocks. We do this Gateau-style verification, potentially rotate transversal gate, potentially put a single qubit gadget on each of the logical qubits, kind of just to increase the amount of gating that's done to kind of be similar to the 5-qubit code example, and then rotate to the measurement basis and then measure out. And then once again, these green boxes indicate where we might have potentially also reduced the fault, varied the amount of fault-tolerant gadgetry used. So after doing all that, you get this kind of I don't know, Pegasus or horse constellation plot. And once again, I'll highlight just a few points. So here's where we're doing fault-tolerant initialization, fault-tolerant measurement out, and we're doing the transversal gate, which is kind of inherently fault-tolerant. And so we get really high fidelities. We get 99.8, 99.9% fidelity for the 2-qubit gate and the X and Z basis, and then 99.4 for the Bell state. Here is the fault-tolerant spam. So that means we're fault-tolerant initializing the code, and then we're fault-tolerant measuring it out. And we get 99.945% fidelity. So that's pretty high as well. So that's pretty cool. And this is bigger, an order of magnitude improvement, I think, from what the numbers Natalie showed, because we're continuously improving the device. And then down here is where we do include those QEC gadgets. They still are injecting more noise into the system than they are helping. It's just that's just they have a certain amount of 2-qubit gates. They're going to inject noise. You only really expect these QEC gadgets to really be helpful whenever you have deeper circuits. So unfortunately, here we're not at the regime, and we're kind of break even with the QEC gadgets, but we're starting to be break even with other things. So in particular, these error rates were so low that we decided to run the same physical version alongside the logical version. And we do indeed see that the logical spam is almost an order of magnitude better than the physical spam. That's great. And then the physical C0 experiments is also doing a bit better than the logical version. Those on the right, far right, those are kind of bounding of the fidelity. These experiments that we did wasn't a full set of experiments in order to do, have a single fidelity number for like process fidelity, but it kind of shows, with these bounds, the logical version is still doing better. This includes both the logical 2-qubit gate and logical spam. We can make arguments for the physical version of the experiment to subtract out the influence of spam, and that improves things. However, it's a little bit more complicated to make those same sort of arguments on the logical level, so we didn't bother doing that. Even in this case where we're kind of preferencing the physical qubit over the logical qubit, we still see that the fidelities are better on the logical level. They might meet exactly at the upper and lower bounds, but even in that case, that's great. And these experiments were done like a year ago, and things have since improved. So if we reran them, I think the separation would probably be higher. And of course, as I said, these things should include these QEC gadgets, because for deeper algorithms, you need to have those in there in order to pump out the faults before they build up into logical errors. So there's more break-even milestones that need to be hit. I think there's probably a huge number of them that, to kind of prove that we can continuously, arbitrarily squash errors for deeper and deeper circuits. But anyway, going with the whole recipe analogy, we continued beyond what the first Steenko paper did by starting to look at 2 logical qubits and doing things on that. Natalie talked about starting to go from looking at doing real-time lookup table decoding to real-time algorithmic decoding for the doing min-weight perfect matching with the surface code and the repetition code, and we're starting to dabble with logical algorithms. But of course, there's way more to do in the future. But yeah, this sort of work really helps to push forward devices, and in particular, like the hybrid compute system was added, to support quantum error correction. So, corporate slide, jobs. If you want, come talk to Natalie, Ben, or myself. And as Natalie mentioned, you can get access to these devices through Oak Ridge or Azure. All right, thanks, and apologies for the technical difficulties.
Okay. Thank you very much for a very nice talk. We now have time for a few questions. There are some hands up there in the back. So you need mic.
Hi, thank you for the very nice talk. I have 2 questions. First, for this WASM thing that you were describing, if either in the future you have faster hardware or if other platforms want to use it, do you have any sense of like how fast the speed of this approach can go? That's one question.
So we didn't invent WASM, just to be clear. WASM is, it looks like you're nodding your head, but for the audience, at least, this is a technology that people are now using in order to run almost natively compiled stuff in web browsers. So it kind of makes an ideal thing to sandbox. So I'm not a software person exactly, although I do a lot of writing of software. But I think as far as there's different implementations of WASM, and I believe it does potentially run at native speeds. Of course, if you really need to run bare metal, then you might want to not use it. But I think it's really close to bare metal given some implementations.
Yeah. And then the second question was, a lot of the stuff you described is all thinking about just the circuits, but one could imagine kind of doing a little bit more lower level hardware co-optimization, either pipelining or otherwise, could give you further gains in performance. Do you have any sense of how much one can really gain from taking more of an approach like that?
Yeah, that's interesting question. We have been focused more on kind of kind of doing doing the various recipes and whatnot, and not really optimizing things. So I think we will move towards that. So I don't have a great answer for how much we will speed up. But looking into things like DD or randomized compiling, as was talked about, or other things, I think we can continue to chip away at it.
Oh, thank you. So I have a question about your encoding, actually a comment. So the encoding of the 513 code that you presented on the slides, it's technically the encoding of the graph code.
Mm-hmm.
representing the 513. But then I was glancing at the paper, then the stabilizers are not the ones for the graph code. So basically the encoding that you have there is fine, is locally unitarily equivalent to 513 from Nielsen and Chuang, but it's not exactly the same code word.
I think it should be. It should produce the logical minus state. We could maybe talk about it offline, but as far as I understand, it should be. And I'd be interested if there's some difference that you spot.
There is a question on that side.
Can you tell us anything about what codes you're going to try to do as you scale up?
Yeah, that will be interesting. Of course, we've looked at the Steam code and color code because they kind of have nice properties in which you have access to all these logical gates transversely. And Natalie's starting to look at like the surface code. A lot of people are into that. And I think, given our flexibility, it might be interesting to look at 3D or 4D codes, as well as look at high rate LDBC codes with more connectivity. Of course, as Natalie mentioned, we can't have like infinite connectivity that slow things down, but kind of like figuring out where the right sweet spot might be. But yeah, we have tons of flexibility, so it's kind of like a great test bed for looking at codes. So that's one problem with our setup, is that kind of there's a wealth of decisions to be made and a big design space. So yeah, we'll be looking at different things.
Hey, so thank you for the very nice talk. So actually, I also have a comment and a question. So comment is that I really appreciate that you didn't do this logical spam correction, because it doesn't really make sense. Okay, then my question is, and hopefully this doesn't come off as like a gotcha question, but so you have this 99.8% 2-qubit gate fidelity, and then your physical spam is like 99.7. Is that right? And then
it's like 99.97 or something like that. Yeah, it's an extra 9, but.
All right, well,
anyway, whatever.
Okay, maybe, probably, okay, but then, so how does the Bell state come out to be 98.7, is what I don't understand? Like, if the gate is, like, are there other errors as well, or is, like, beyond spam, like, is it also, like, single qubit gates, or, like?
So, yeah, you're talking about the physical.
The physical, yeah.
So, yeah, there's a variety of things. One of the major contributors is potentially the memory error, because like we do have effective all-to-all connectivity, but it's not it does have memory error that's incurred by transporting things around. So maybe some of that's what you're talking about. The overall error rate of like the things that I was showing was mainly like for the entire algorithm. It wasn't like just the 2-qubit gate. So there's like spam plus that plus memory error.
I see. So it's not just put 2 qubits together, make a Bell state. It's like there's also some movements and like all these. I see.
Yeah.
Okay. Cool. Thanks.
Mm-hmm.
Okay, maybe we can take a quick online question. So question is there a continuum future hardware vision for scaling beyond a single chip?
Yes, Natalie had some nice slides where they kind of alluded to that. I am a theorist and not an experimentalist, so I don't know all the details, but essentially it's the same sort of idea that I think most others have, that you build out the chip, like for us, the 2D grid as far as you can. That seems reasonable. And then you have these modules, and you might use like photonic interconnects or other methods in order to kind of glue them together. So I think that's a common kind of theme, and the industry will be needing to face how to connect modules together in the same way.
Great, thank you. So I guess I can see there are a few more questions coming up. So I encourage you to have a chat with the speakers in the lunch time. In the interest of time, we conclude this morning session, and let's thank all 4 speakers again for their fantastic talks.
Thanks very much, Usman, and thanks everyone for a great morning session. So lunch is now provided, so you can eat here at the tables. We have an hour and a half, so we're back at 1:30. I encourage all of you who just flew in on a 24-hour flight yesterday to get out and move around a bit. It will do wonders. There's a nice walk along the water here, and also if you just go down here through the park, there is a ferry. That's the sort of the public transport ferry, and that goes all around the harbor for rock bottom harbor cruise prices. I would just warn you all, though, it is now over 30 degrees Celsius outside, and the sun is blaring. It's very intense, so put on a hat, put on sunblock, watch the sun if you are going to go outside. We'll see you all back here at 1:30 p.m. Thank you very much.
Just very quick announcement. Those who have their talks after the lunch,